As a consequence of the work we did in sections 3.1 and 3.2, we now have a pretty good understanding of how derivatives handle the four arithmetic operations. In other words, addition, subtraction, multiplication, and division. In the case of addition and subtraction, derivatives just break up nicely. But when it comes to multiplication and division, well, we have the product rule and the quotient rule to handle those cases. But what about composition? In other words, what if I take two differentiable functions and I form their composition? Can the derivative of this new function be obtained in terms of the derivatives of the original two functions that I started with? That's a reasonable question to ask, and the short answer is, well, partially. And the more thorough answer, well, that requires the chain rule, and that's what this section is about. So I'm going to start by just introducing you to what the chain rule is. And you can see the idea is motivated here with a little bit more of a concrete version of what I just said in the opening. So let's say we had two functions, f of x given by the square root of x, and g of x equal to 3x to the power of 9 plus 5. Now, on their own, we have the tools to take the derivative of both of those functions. Right? We can write f of x, you can write it as x to the 1/2 and do the power rule. G of x is a polynomial, so you can just split it up term by term and use the power rule in each term. So the derivatives of those two functions are well understood. And if I multiplied them and created a new function by multiplying these two functions, f and g, well then we could use the product rule to take the derivative. If I put these two functions together using division, well, I could differentiate the result using the quotient rule. But the question is now, what about the composition? What if I take f composed with g? And that's the question that this section is going to answer. And in general, we can say the following. So this is the rule that we'll use to differentiate functions of this form when you have the composition of two functions whose derivatives you already know. So here, this is called the chain rule, and it says the following. If I want to take the derivative with respect to x, I'm going to use operator notation to phrase this. If I want to take the derivative with respect to x of the composition of f of g, so in other words, I want to differentiate f of g of x, well, it turns out I can do the following. It turns out I can first take the derivative of the outside function, f, right? Because if I write this expression down, f of g of x, really g is the inside function and f is the outside function. So I could start by taking the derivative of the outside function, and then what I plug in is g of x. And that's not the whole story. I still also have to multiply now by the derivative of g. So multiply by g prime of x in particular. And that is called the chain rule. So well, first let's put a box around this, because this is a really important rule. So you want it to stand out as important. So add this to your formula sheet if you're making one. And this is called the chain rule. Okay, so that is the rule that we're going to use to differentiate functions that appear in this form, that appear as the composition of two other functions. And this rule kind of comes with a couple of requirements. Okay, so I've started a note here that we're going to finish off momentarily, and it says this rule is only valid for values, for real numbers x, that's how you can interpret this, but for values of x in the reals such that the following two conditions hold. And really you can recover these conditions just by looking at the right-hand side of this formula. So the first condition is, well, looking over here, you can see that g prime of x appears in the expression, right? We've written down g prime of x as part of the formula for computing the derivative of this composition. So if in order for g prime of x to make sense, you really do need g to be differentiable at x. So we need that first and foremost. So g is differentiable at the point x. That's the first requirement. And what else do you notice? Well, there's another derivative in this expression, and that is f prime. You see that the derivative of the outside function f is calculated and then evaluated directly at the point g of x. So for this for this first factor to make sense, we also need f to be differentiable, not at x, because we're not plugging x into f prime, we're plugging g of x into f prime. So we actually need f to be differentiable at g of x. So those two conditions are really what you need in order for the chain rule to apply. But typically in situations where you're applying the chain rule, you will have these true. They'll quite often, they may not be addressed explicitly, but they will be true in the background in all cases when the chain rule is actually relevant. Okay, and remember there's lots of different notations we used for derivatives, and in the case of the chain rule, sometimes you might want to express it using some of those other options. So remember Leibniz notation is it's that notation that looks like a fraction of differentials. And I'll remind you of it just momentarily here when we write the alternative phrasing of the chain rule. So instead of, it's all already up the screen, instead of writing the chain rule down like this, which for those of you who like this manner of using the chain rule, just write it down this way. There's nothing wrong with just writing it down that way. But some of you might like to have another version handy, and this is another way you can write it. So if you had y as some function of a variable u, so in other words, if you've got y is equal to f of u, and then you had u, this variable u happened to actually also itself be a function of some other variable x, and if we add another assumption that this function f and this function g are also differentiable, then you can phrase the chain rule in the following way. You can say that the derivative of y with respect to x, so this is just a reminder, this is an example of Leibniz notation, so if you hear that phrase, we're just talking about writing your derivatives using this notation. Well, so if y is a function of u and u is a function of x, you can write the derivative of, well, let me back up a bit. If y is a function of u and u is a function of x, then really if you compose those two functions, then y is actually also a function of x. So it makes sense to write down the derivative of y with respect to x, and you can compute it in the following way. First, just take the derivative of y with respect to u, right? Because y is a function of u, so it makes sense to do that. Really, this is just another way of saying f prime of u. But don't stop there. You're also now going to multiply this by du dx, right? This is the derivative of u with respect to x, which makes sense because u is a function of x by assumption. So really, this is just really g prime of x. And another way of writing g prime of x. So really, this is just an alternative phrasing of the chain rule. But a lot of people actually find this a little bit easier to remember, and here's why. If you look at the right-hand side, these symbols here, dy, du, it's not really a fraction. And du, dx, it's not really a fraction either. This whole symbol, this whole piece of notation is one symbol. Same with the dy, du, it's one piece of notation. So we just got two quantities that we're multiplying. They're not really fractions. But it certainly helps to think of them as fractions sometimes, especially if you're trying to remember this rule or remember why it works. If you were to temporarily think about these as fractions, what would you notice? You'd probably see the du on the numerator over here and a du on the denominator over here. And if you canceled them, what would you get on the right-hand side if you were to cancel the du's? You can't really do it. Technically, you can't do it, but it certainly is a nice memory tool to just imagine if you could. Because if you could do it, what would you get? You'd get dy over dx, which is what's written over here. So if you were just to allow yourself the flexibility to think of these derivatives as fractions, then you can recover the chain rule just by thinking of this as cancellation. But I do want to emphasize that they're not actually fractions, so we're not going to actually do any of that cancellation, but it's a nice memory tool. So let me just also add, just to make it clear, this is also the chain rule. It's just expressed differently. Okay, so that's another phrasing. All right, well I've kind of just gone over the actual rule in two different forms, and we've set a couple of requirements that have to be true, but let me now show you how to actually use this rule. So here's an example where you would do that. So we've got an example that's asking us to find capital F prime of x, where capital F of x is given by this function here, which this is a composition of two functions, right? We've got an inside function, x squared plus 1, and the outside function is the square root function. So this really is a composition of two functions. So the chain rule is going to be exactly what we need here. Okay, so first let's start by spelling out exactly what the composition is. So let's write the following. We'll write capital F of x. let's write this as a composition. We'll write this as little f of little g of x. Do I need to use little f and little g, or could I use any letters I like for these functions? Absolutely. I just got to be consistent with whatever I start with. But let's use f and g. And what would they have to be in order for this equation to be true? Well, the inside function g of x is going to be that inside function x squared plus 1. So let's say g of x is equal to x squared plus 1. So that's the inside function. What about the outside function? It's that square root, right? So let's say and f of x is just equal to the square root of x. And if you take their composition, if you take f of g of x, you're going to get exactly this function up here. So that's a valid decomposition. So I need to get a bit more light. Not sure if that helps, but I forgot to turn the light on, so I'll add it on now. Okay, well, let's actually write the chain rule out then. So we wanted to find capital F prime of x. And I do this sometimes when I introduce a new rule. I like to just reserve one step for just switching notation. So I'm going to change this from capital F prime of x to the derivative with respect to x of, well, what are we really taking the derivative of? We're taking the derivative of capital F of x, which is just the same as little f of g of x. So I'm going to write little f of g of x inside there. Okay, why am I doing that? Just because I want to make it really look like the left-hand side of the chain rule, which is up here. So we literally have exactly this showing up. We just have specific functions f and g. So what's this going to evaluate to? Exactly what the chain rule tells us, right? It's going to be this expression here. So let's start by applying that rule and just have, we'll write f, little f prime of g of x times g prime of x. Okay, so now it's just a matter of gathering the ingredients, so to speak. We've got the recipe right here. It's telling us how to build the answer. We just got to get all the parts and put them together properly. So in particular, you notice that both f prime and g prime appear in this expression. Now g prime just has x plugged in, so this is just literally going to be g prime of x, whatever the derivative of x squared plus 1 is. But this one over here, the f prime of g of x, it's not f prime of x, it's f prime of g of x, but we're still going to need to compute f prime. So let's start by working out what f prime of x is and what g prime of x is. So, well, if f of x is equal to the square root function, over here we've got f of x is equal to the square root of x. Remember, you can write this as f of x is equal to x to the 1/2 and just do the power rule. And you'll get 1/2 x to the negative 1/2, which if you change it back to radical notation and get rid of your negative exponents, you'll end up getting 1 over 2 times the square root of x. So that's what you get for f prime of x. And g prime of x, well, g prime of x is just the polynomial x squared plus 1. We can just do the power rule on each term. So we'll get 2x for the derivative of g. So that's our two derivatives, f prime of x and g prime of x. But in our answer over here, remember, we don't want f prime of x as our answer. We want f prime of g of x. So that's no problem. All we have to do is just take g of x and plug it in here, right? Plug g of x in here, and that will be f prime of g of x. So we want f prime of g of x. Well, it's really, if I were to write it out in a literal sense, I would have 1 over 2 times the square root of g of x, right? That's literally what f prime of g of x means. But g of x is x squared plus 1, so why don't we substitute that in for g of x, and we'll get 1 over 2 times the square root of x squared plus 1, right? This is our f prime of g of x right over here. So this expression is what we're going to put in for here, and then g prime of x is what we need for this part here. So we have everything we need, right? And let me just, I don't want this to get confusing here, so I want to just box this off to separate the details. Down here is just details where we compute the smaller pieces, but up here is our main thread where we're computing the derivative of capital f prime of x. So we'll keep on going with this calculation by substituting everything that we need in here. So here we'll put this in for f prime of g of x. We've got 1 over 2 root x squared plus 1. And then it's going to be multiplied by g prime of x, which is 2x. So we'll multiply that by 2x here. And then really, we can clean this up a bit. Really, this is 2x over 2 times the square root of x squared plus 1. And you can cancel the 2's, and that's about as much as you can do. So you end up getting x over the square root of x squared plus 1. So that is our capital F prime of x. So that's an example of using the chain rule. Now, using this strategy, I had to actually write out our function, capital F of x, as an explicit composition of two functions f and g. And what ends up happening is you can see that there's a lot of notation here that I've written down to compute a derivative that a lot of other people that have done this before might do this a lot quicker and have it much more streamlined. And in general, that's what you do. So this step here where I actually wrote out capital F of x as a composition for two explicit functions that I write down, quite often in practice, once you master the chain rule, you won't actually do this step. You'll do it on the fly without actually explicitly writing it out. And what ends up happening is that a lot of this notation gets cut down, and it just makes it a little bit more approachable. So I'll show you how to do that on the next page.